So here in this video, I will be defining sum of products form, product of sums form, and their respective canonical forms. So I'm starting off with sum of products form. Sum of products form is exactly how it sounds. It is the sum of two products. So here in my example, I have T equals AB plus complement of CA. And that is how I would say it in if I were explaining this to someone who hasn't taken this class before. In reality, you have A and B ORed with complement of C and A. And I've drawn out the circuit to help demonstrate and define this a bit further. So AND gates represent multiplication in this class, or digital design. So here you see I have A and B. These variables are being multiplied together in the AND gates. And down here I have complement of C being multiplied in this AND gate with A. And then these respective terms are being ORed or added together in this OR gate. So you have A being multiplied with B, added with the term of complement of C being multiplied with A. So similar to just standard algebra that everyone kind of grows up learning. So from here, you can derive the canonical sum of products form from that equation. So here I have said equation. Here I have T equals ABC plus A and B and complement C, ORed with A and complement B and complement C. So canonical sum of products form has every variable total in each min-term, a min-term being the product terms. You can see here everything it's multiplied, so it's product. So, well, it turns into this form, of course, but anyways. So to get this equation, what you have to do is you take this original equation, just the SOP form, and expand it. And to do so, you need to use the distributive law. So you look at, I have the work shown here actually. So here's the original equation. So what you need to do here is you look at the first term. I have AB. What is this missing when I look at the output term? So looking at the next term, I see we have A in common, but it doesn't have C. So what you'll do is you go to this first term and you will distribute that term, multiply it with the standard form of that complement term, as well as the complement term itself. So you distribute A and B with C or C's complement. And you do the same thing for the next term. You have complement of C and A. What is that missing? It's missing the B. So you'll go ahead and bring over that B and its complement form and distribute. So you have that here in the second line where I demonstrate such. I have AB being distributed. So kind of bringing in algebra terms, non-digital design algebra terms. So you'll distribute, and you can see here in this third line, I have everything distributed out. So I have A and B and C being added with A, B, and C's complement. And then from this term over here, I have, and I wrote this in order, of course, I have A, B, and C's complement added with A, complement of B, and the complement of C. And then you just need to be sure you cancel out any common factors, but you just keep the one. It's similar to kind of like the AC method in algebra, where when you're looking for similar terms, you'll cancel out the final terms. It's a bit hard to explain, but it's similar to the AC method in algebra when you're trying to get your final answer. But I'm not explaining at standard algebra. I'm trying to explain digital design. Come on, Caitlin. So here we have A and B and C. So that is not copied at all, so we leave that one alone, drop it down. I have A and B and complement C. That is here twice, so you will just cancel out one, bring down the next, and I have A and complement B and complement C. So I just have those three terms left, and I get the final equation being canonical sum of products form. What's great with canonical form is that you can easily create your truth table from this. Since everything here is in its min-term, you just need to remember that min-terms, with its original variable being just this standard A and standard B and standard C, these have the value of 1. Anything complemented has a value of 0. So just keep that in mind when creating your truth table. As you can see, if I had created a truth table, I would have 3 true outputs. And every term you get in this final equation here represents a truth in that truth table. And here I have product of sums form. So my equation is going to be T equals A plus B multiplied with A plus complement of C. Or in digital design terms, it's going to be A or B ANDed with A and complement C. And here I have the circuit showing how you can derive said equation. So here I have 2 OR gates and an AND gate. So OR gates, as said before, represent addition, and AND gates represent multiplication. So product of sums form is just, it's reversed. Sum of products form is the sum of 2 products, and here you have the product of your 2 sum terms. So as we can see here, I have A plus B, this OR gate, and I have A plus the complement of C. Those 2 terms get multiplied against each other within this AND gate, giving you T equals A or B ANDed with A or complement of C. So down here I have the Cpos canonical product of sums form, and similarly in definition, at least, it's the same. Canonical forms are just the extended versions of well, I guess here, because we're dealing with OR terms, everything here is in its max term, but in the canonical form, you have every variable present. So to get canonical product of sums form, it's not similar to how you can get canonical SOP form. So in SOP form, you distribute missing terms. I guess you can say in a similar way, you do the same here. So let me walk you through my work. So I have T equals my given equation from up here. I have T equals A or B ANDed with A or complement of C. And you have to look in each respective term and see what it is missing. So I have A or B that is missing complement of C. So similarly to SOP form, you'll bring over C ANDed with complement of C being ORed with B, ORed with A. And same thing on the other side. You have A or B, because it's missing B in this term, ANDed with B complement, ORed with C complement. And from there, you just branch off into separate terms in a way. So here in this term, this breaks down to two separate terms. So the first one, you have A or B or standard C. And in this second form, you have A or B and A or B or complement C. And then to make it simpler, I just remember that separate from this other term, I drop down this little and term, but of course there's an invisible and term in these two areas as well. So let me erase this for now to make it a bit more simpler. So here it breaks off into its first separate term. I have A or standard B or complement of C. And over here you have A or complement B or complement C. And similar to Csop, you have to get rid of any common factors. So as we can see here, I have A or B or C. There are no dupes, so leave that alone. Drop it down. I have A or B or complement C. I have two of those terms, so I will cancel one out and then drop the other. Last term, I have A or complement B or complement C. So there are no dupes for that, so you just drop that down, giving you this final term. And like with Csop, with Cpos, you can easily create the truth table, but you just need to remember that the values for the max terms are different from the min terms. Min terms are an original variable, has a value of 1, and the complemented variable has a value of 0, but with its max terms, it is quite the opposite. So with max terms, the original variable, it is assigned a 0, and anything complemented, it is assigned a 1. So in my truth table, if I had created one, I would have 3 true outputs being 0, 0, 0, and 0, 0, 1, and 0, 1, 1.